Welcome everybody to our next installment of partial fraction decompositions for integration. So we knew that in our partial fraction decompositions, we were going to really have elements that are kind of the form of either some constant over a linear factor, x minus a to the n power, or we were going to have something along the lines of maybe a linear factor, bx plus c, over an irreducible quadratic, ax squared plus bx plus c, maybe that to some other power. And so the question really then becomes, what do the integrations look like at that point? So once we've done all of the partial fraction decomposition, we've done the work, we've solved the system, we've gotten things down, and so now we're kind of at our last step of what do the actual integrations look like. And so for that, let's take a couple of examples and just kind of go from there to see especially what's going to happen with the irreducible quadratics. And so kind of our most simple case that we could really deal with is when we just have linear factors and maybe linear factors with a repeated multiplicity so that we've got some powers. And what really happens there is we can tell in this situation, when we've got just an x minus 1 in the denominator for that power, now our integral is really just going to look like the natural log. And in the situations where we have some power to some linear factor to a power, now we're really just back to the power rule to evaluate any of those integrals. And so what would happen at this point, we would really say that the integral of 2 over x minus 1 is going to give us 2 times the natural log of the absolute value of x minus 1, plus, and then for our other factor, we've got 3. If we increase that power by 1, then that's going to give us a negative 1 over x minus 1 to just the first power. And then plus our arbitrary constant. And so for those situations, our integrals really are not too bad. We don't have to do a lot of work, and everything is pretty straightforward. Now, when we come to the irreducible quadratics, things get a little bit messier, but not much more difficult. And so kind of the idea with our irreducible quadratics, when we just have constants on top, then those really just, our idea is really just to use completing the square. Completing the square will then get it transformed into something where basically our integral will look like an arctangent of some expression. And to kind of see what that would look like, well, if we take this example where we have our 2x squared plus 2x plus 5 in the denominator, if we complete the square on that, so we start off with x squared plus 2x plus 5, we're matching the form x plus b quantity squared being x squared plus 2bx plus b squared. And so in this case, what do we have? 2b is going to be 2, so b is just going to be 1, and in particular, our b squared is also just going to be 1. And so for this expression, we would then have our x squared plus 2x plus our new constant 1, and then just to keep things balanced, we add 1, we subtract 1, and then we take the constant that we already had. And so when we group those first 3 factors together, we know that that will factor as x plus 1 squared, because that's how we designed it, and then the minus 1 plus 5 becomes a plus 4. And so in this case, this is really what we're going to use. We're going to use our completed square form to then probably do a u substitution to then make it look like an arctangent. So then rewriting our denominator in our perfect square form, or completed the square form, now if we would do a u substitution with u is equal to x plus 1, so that du is just still our dx, our integral then becomes 1 over u squared plus 4 du. And for this, if we then wanted to take it kind of one step further and factor out that 4, then what would happen, we factor out a 1/4 in the denominator, so we get a u squared over 4 plus 1 du. Or if we just combine that into the square, then we have u over 2 squared plus 1 du. If we wanted to, we could then do another u substitution and say maybe w looks like u over 2, so that dw looks like 1/2 du. And so in this case, what does our kind of final integral become? It becomes a 1/2 or 1/4 times our du, which is going to be a 2 dw, all over w squared plus 1. And so we're really just doing an integral of 1/2 integral dw over w squared plus 1. And this we do recognize as just being our arctangent. And so what we have in this case is that we've got our original integral 1 over x squared plus 2x plus 5 equal to our 1/2 the integral of 1 over w squared plus 1 dw, where we had made the substitution that u was going to be x plus 1 and w was going to be u over 2. And so what this gives us is the integral of the arctangent of w plus our arbitrary constant, and then 1/2 going back to u, our arctangent of u over 2 plus c. And then finally, if we go all the way back to x, we get a final answer of the arctangent of x plus 1 over 2 plus our arbitrary constant. And so when we just have an irreducible quadratic to the first power, probably doing a u substitution, completing the square, to then do a u substitution or maybe a couple of u substitutions, and we can make our final answer look something like an arctangent. So now let's examine the case where we've got an integral of just our 2x plus 3 over x squared plus 4x plus 9. So we've got a full-blown linear factor on there. So not just a constant in the numerator. So how do we deal with that? Well, the idea is that we can separate that out into two separate integrals. So we've got a 2x over x squared plus 4x plus 9 dx plus an integral of 3 over our x squared plus 4x plus 9 dx. And so the idea is, can we do some kind of u substitution on the first integral, because we almost have a first power of x, or we almost have the du in the numerator on top when we have our dx. And so the question is, can we kind of do something to make this also look like a u substitution? And the idea is that we can, and what we can do then at that point is to imagine that we were doing a u substitution with u is equal to what our denominator is. So x squared plus 4x plus 9. So that our du is then going to look like a 2x plus 4 dx. Okay, so now what we're missing is that on top we had a 2x plus 3, but what we needed was a 2x plus 4. And so how can we rewrite that so that we have a 2x plus 4 on top? Well, the idea is that we're just using our old trick of adding something and subtracting something. So right now we have a 2x plus 3. We need a 2x plus 4. So we add on 4, and then so that it stays balanced, subtract 1 on there. Now, what this will then give us is this part will end up looking like a du, and this is the integral that we end up splitting. So the plus 4 minus 1 is going to give us that plus 3 in our original integral. So everything is staying balanced. And now when we split them up, it looks like a 2x plus 4 over our x squared plus 4x plus 9 dx minus an integral of 1 over x squared plus 4x plus 9 dx. For the first integral, we can do our u substitution, so that integral now looks like a 1 over u du. And then for the second integral, we still have just our x squared plus 4x plus 9 dx, for which what we do with this, we complete the square. To then yield something involving something that will end up looking like an arctangent. So again, completing the square, we had our x squared plus 4x plus 9. Well, if our 2b was going to be our coefficient of x, so we had 2b being 4, so the b was going to be 2, and then b squared was still going to be 4, then our integral actually, or our quadratic, looks like x squared plus 4x plus 4 minus 4 to keep things balanced, and then we had our original constant of 9. So that grouping those first three together, we have x plus 2 squared, and then minus 4 plus 9 is going to give us a plus 5. So that our integral is then going to be our integral of 1 over u du minus our integral of 1 over x plus 2 squared plus 5 dx. And so now at this point, we could do a substitution onto the second integral to maybe make this something like, if we kind of wanted to put those two substitutions together, what would it look like? Well, I can pull out a 1/5 in the denominator of the second integral. So if I do that, now I'm going to have a 1 over and put it inside that quadratic so that it really looks like our x plus 2 over the square root of 5 squared plus 1 dx. So that now when I do my substitution with something that looks like, say, w equal to x plus 2 over root 5, then dw looks like a 1 over root 5 dx, or the square root of 5 dw is my dx. So that my integral will look like my integral of 1 over u du minus my 1/5 integral 1 over w squared plus 1, and dx looks like the square root of 5 times dw. And so I have, as my integrals to actually do, 1 over u du minus a root 5 integral of 1 over w squared plus 1 dw. So this ends up giving me a natural log of the absolute value of u minus the square root of 5 times the arctangent of w plus our arbitrary constant. And so kind of going back to our original substitutions now, we had u equal to x squared plus 4x plus 9. And then for w, we had w equal to our, we had w equal to our x plus 2 over root 5. And so for our final answer, we get something that looks like the absolute value of x squared plus 4x plus 9 minus the square root of 5 times the arctangent of x plus 2 over root 5 plus our arbitrary constant. And so maybe as one final example, we can say, what happens if we had an irreducible quadratic to a power in the denominator? Well, not really much changes at that point. Our first step is the same as it has been before, that we just complete the square. So that if we have x squared plus 2x plus 7, well, we've got 2b being our 2. So b is going to be 1, and so b squared is going to be 1. So this gives us a quadratic x squared plus 2x, our new constant, plus 1. Then to keep things balanced, minus 1, and then our original plus 7. So that we had x plus 1 squared minus 1 plus 7 gives us a plus 6. And so really, we are looking at the integral of x plus 1 squared plus 6 squared dx. And so our first step to kind of begin cleaning things up, if we wanted to do our kind of transformation on this one, we can factor out a 6 from that, factor out a 6 from our denominator. And really, when we factor out the 6, it will be a 6 squared because of our power that's there. So we're really factoring out a 1 over 6 squared. Our integral 1 over, and then we'll have our x plus 1 over the square root of 6 squared plus 1 squared dx. And so our kind of first substitution is then just going to be our u equal to x plus 1 over the square root of 6. So that du then is just going to be a 1 over root 6 dx. And so with our substitution of x plus 1 over root 6, we have our integral then becoming 1 over 36, integral 1 over a u squared plus 1 squared, and then for our dx, we just have the square root of 6 du. And so what we end up kind of simplifying, or what we have to work with, is our 36, we have 6 squared, and so really this is going to be a 1 over 6 to the 3 halves when I take out that root 6 that's there. So I get 1 over 6 to the 3 halves, and then my u squared plus 1 squared du. And so what happens at this point? Well, we really have everything set up for a trigonometric substitution. And since our form looks like a u squared plus 1, what we have in that case is just going to be u equal to tangent of theta. So then with our substitution of u being tangent of theta, our u squared plus 1 then becomes tangent squared of theta plus 1, and that becomes our secant squared. Likewise, our du becomes derivative of tangent, which is going to be secant squared of theta d theta. And so our integral then becomes a 1 over 6 to the 3 halves integral of 1 over u squared plus 1 becomes a secant squared, and then for my du, it becomes likewise a secant squared, theta d theta. And so what I end up integrating at that point, I get a 1 over 6 to the 3 halves integral of my secant squared of theta on top, secant to the 4th of theta on the bottom, d theta. So I get a 1 over 6 to the 3 halves integral, cancel each one of those. I have a 1 over secant squared of theta d theta, but 1 over secant squared is the same thing as cosine squared of theta d theta. And so what happens now? I have a trigonometric integral. Doing a trigonometric integral with something like this, we just use our power reduction formula at that point. So for these guys, we really have power reduction. And so our integral becomes a 1 over 6 to the 3 halves integral of, with our power reduction formula, 1/2 plus 1/2 cosine of 2 theta d theta. And so our integral, a 1 over 6 to the 3 halves, I have a 1/2 theta plus a 1/2. So I'll have a sine of 2 theta. And then my chain rule would give me a 2, which I kill that off with another 1/2. And then finally, my arbitrary constant. And so I get a 1 over 6 to the 3 halves, 1/2 theta, plus 1/4 sine of 2 theta, plus c. And so now begins the job of unraveling all of this. So we have 1 over 6 to the 3 halves. We've got our 1/2 theta. And in our sine of 2 theta, we can use our double angle identity for that one to say that one is going to be 2 sine of theta cosine of theta all over 4 plus c. And so we end up with a 1 over 6 to the 3 halves, 1/2 theta, plus a 1/2 sine of theta, cosine of theta, plus c. And for this, now we go back to our right triangles. And so our trig substitution was u equal to the tangent of theta. And so the tangent of theta, if I then draw my right triangle, tangent theta is going to be the opposite over the adjacent. So this looks like a u over 1, and my hypotenuse then just looks like 1 plus u squared, square root of all of that. And so what this then gives us is that the sine of theta is going to be the opposite over the hypotenuse. So u over the square root of 1 plus u squared. And likewise, cosine of theta is going to look like 1 over the square root of 1 plus u squared. And so in my substitution, if u is going to be tangent, then u is going to be the tangent of theta. What happens at that point is I have a 1 over 6 to the 3 halves. 1/2 theta becomes a 1/2 arctangent of u plus a 1/2. Now my sine times cosine ends up looking like a u over the square root squared, so that looks like 1 plus u squared plus c. And so we're almost there. We just got to get back to our original x. And for that, we remember our substitution. And that one was u is equal to x plus 1 over root 6. And so if we substitute this back into our original expression, what do we obtain? And so our original integral was the integral of 1 over x squared plus 2x plus 7 quantity squared. And so now our final kind of substitution that we were doing, we said that u was going to be x plus 1 over root 6, which then told us that our final answer was going to be something of the form 1 over 6 to the 3 halves, 1/2 arctangent of x plus 1 over root 6 plus 1/2 of x plus 1 over root 6 in the numerator and x plus 1 over root 6 squared plus 1 in the denominator plus our arbitrary constant. And so this gets us back to our original expression involving our original variable x, and finally gets us to an answer. So through lots of twists and turns, a trig substitution, then a trigonometric integral with a power reduction, and we finally get down to our answer. So a little bit more involved and potentially some kind of twists and turns as we get through there, but with all of the skills that we've had with our techniques of integration up to this point, everything is totally manageable. So I hope you've enjoyed this, kind of going through some of these examples, and I will see you guys next time.